Hi, hello, welcome. This is Discrete Mathematics, and today we are talking about section 1.6, nested quantifiers. Start off with this statement. The sum of two positive numbers is greater than 0. Let's think about that statement. Do we think that's true? Two positive numbers, you add them together, you're going to get something that's greater than 0, which is also positive. So yeah, I think that's true. Let's write it a little more formally. For every x and for every y, if x is greater than 0 and y is greater than 0, so these are our two positive numbers, then x plus y is greater than 0. That's their sum. The domain of discourse is r times r cross r. This is the Cartesian product, which we learned about in a previous section. So we can say that that's r cross r. We can also say that that's r squared, because r times r would be r squared. That's our domain of discourse. In using even more symbols, we can write x is greater than 0 and y is greater than 0 implies x plus y is greater than 0. Let's let p of x denote that thing that I just said. Then we can write the expression as for all x and all y, p of x, y. So for every x and every y, this statement is true. If x is greater than 0 and y is greater than 0, then x plus y is greater than 0. Our domain of discourse is r squared. So we've used multiple quantifiers here. We've used the for every quantifier, but we've used it twice, once for x and once for y. When you use multiple quantifiers, they are said to be nested. So we can use nested quantifiers. The different combinations that we'll see are for all x and for all y. We'll see for all x there exists some y. We'll see there exists an x such that for all y. And we'll see there exists an x and there exists a y such that something is true. We are only going to deal with the case where we have two quantifiers together, but there are more. You can extend this idea further, but this is all that we're going to do in this class. Let's look at some more examples. Express in predicate logic using the following predicates. Predicate is another way to say prepositional function. Propositional function. So here are our propositional functions. B of xy, x is a brother of y. S of xy, x is a sibling of y. And L of xy is x loves y. So in part A, we have brothers are siblings. So let's see. B of xy, if x and y are brothers, then x and y are siblings. So b of xy implies s of xy. Another way we could write it in words is if x and y are brothers, then they are siblings. And if I write this version, it's a little bit easier to see the predicate logic version. All right, next one, everybody loves someone. So everybody, I'm going to start to see some quantifiers here. Everybody is going to be for all, and somebody is going to be there exists. So let's maybe write this out in words before we write it out with symbols. Everybody loves somebody. So for all x, there exists a y. There exists a y such that x loves y. Close my parenthesis. For all x, there exists a y such that x loves y. That's everybody loves somebody. So we can write that out. For all x, there exists a y such that L of xy. All right, let's take a look at the next one. Everybody loves everybody. So here is, oh no, sorry, I'm writing everybody, maybe think of E, but no, everybody is for all and everybody is for all. So I can use a very similar thing for all x and for all y, x loves y. For all x and for all y, L of xy. Next one, there is someone who is loved by everyone. So there is someone who is loved by everyone. Maybe I'll write this one out in words. There exists x such that for all y, x loves y. So this is saying something a little bit different than we had in part B. In part B, we said for every x, there exists somebody that x loves. And here we're saying there exists an x that is loved by everybody. Those actually are two different statements. And we're going to see that in the order here. There exists an x such that for all y, L of xy. So here we see that these two are actually different statements. The order of for all and there exists matters. You can't just change the order or you'll get a different statement. All right, let's look at the next one. There is someone who loves someone. So here we've got the double E. There exists an X such and a Y such that L of XY. Somebody loves somebody. And last one, everyone loves himself. So we're going to do it for all, but we're talking about himself. So X loves X. So for all X, L X, X. X loves, not somebody else, X loves that same person. So that's the same X. So in this way, we can use these nested quantifiers to talk about multiple or functions that take on multiple values. How can we deal with negation when we're looking at these nested quantifiers? Let's do a little review over here of negation. Let's see, negation with numbers. If we have a minus sign, we would, and we had inequality symbols, we would change the inequality. If we multiply or divide by a negative number, we change the inequality. For sets, our negative is this one. That's the complement. Complement. According to De Morgan's law, if you take the complement of a union or an intersection, those get switched. So union and intersection get switched when you do the complement. When we have logic, which is what we're dealing with right now, the not symbol changes and to or, and it also, we saw in the last section, it changes for every into for some, or there exists. So that's what we're going to see happening here. I'm going to distribute this negative to all of these things. And so I'll have a for every x, there exists an x such that for all y, not p of x, y. I could do a similar thing down here. This is for all x, there exists a y such that not p of xy. So this is how I deal with negations. It's an extension of the negations that we saw last time. All right, let's do a negation example. This is example 2. I'm going to distribute this negation. Let's see, I'm going to have for all x, there exists a y such that not xy is less than 0. And I can actually simplify this not xy is less than 0. For all x, there exists a y such that x times y is greater than or equal to 0. That's my new statement. Okay, we're going to be working more with these nested quantifiers. And so we have a table here that helps us determine, I want to show whether a statement is true or false. What should I do? We saw last time to show a for all statement true, I have to prove that, and that can be difficult. But to show it's false, I have to find a counterexample. So that's what this table is saying. I noticed there are more rows, and that's because there are more combinations. This first row and this last row are the ones that we're going to be familiar with already. So we'll talk about the first row. For all x and all y, or the order of this one actually doesn't matter. For all x and all y is the same as for all y and all x. P of xy is true. In order to show that this one is true, you have to prove it's true for all x and all y, using algebra, logic, things like that. So this case is a little bit harder, and we're going to see an example of this one. We're actually going to see an example of, there's 8 boxes here. Here we'll see examples of all of those. To show that this one is false, you just have to find a counterexample. One x and one y together that make p of x false. Sometimes when we're looking at this false column, it can be easier to show that the negation is true. And that is a way to show that the statement is false. If the negation is true, then the original statement is false. So sometimes some students like to think about that. I'm trying to show that the negation is false. And the negation for this one would be there exists an x and y such that p of x is not true. And that's exactly what we're doing. We're finding one x and one y such that my p of x is false. That's a counterexample. So let's jump down there. That's this one. So in order to prove there exists an x and a y such that p of xy is true, you have to just find one example where it's true. Maybe there is only one example. Maybe there's more than one example. You only have to show one. It's not called a counterexample because you're showing it's true, but that's what it's called to show the first one was false. And again, the order for this one doesn't matter with the double E, double backwards E. However, to show that this one is false, then I have to show that it works for every x and every y, that p of x is false. So I'm kind of going back up here. I have to prove that for all x and all y, p of x is false, which can be a little bit more difficult. So here's another proof one. These ones are the proof ones. These ones are the example ones. So these two are so far an extension of what we saw last time. We'll talk about the other cases as well, maybe as they come up. I think we should get into some examples. The first example is example 3a. So here we are the double for all. So is the statement for all x and all y, x is greater than 0 and y is greater than 0 implies x plus y is greater than 0. This is the one that we saw at the beginning. Two positive integers added together is something positive. So this one we think is probably true. I'm going to put my guess up here in green with a little question mark, and that'll help me determine what I should be trying to do. So I want to try to prove that this is true. So let's see, I'm going to start with something that I know. For all x, y in R, that's my domain of discourse, I'm going to say, well, x is greater than 0 and y is greater than 0. That's the premise. That's my if statement, that that's true. So let's add this row together. So I'm going to add my left-hand side. That's going to be x plus y is greater than 0 plus 0, which is x plus y is greater than 0. And that's my conclusion. That's this right here. So I've shown that if we are given that these first two things are true, then it follows that this x plus y is greater than 0 is also true. So that is my proof for this one. And that was this box. So I'll say this was 3a. We did an example in this box. Let's look at B. Is the statement for all x and all y, x is greater than 0 and y is greater than 0 implies that x is greater than 0 and y is less than 0 implies that x plus y is not equal to 0. And my domain of discourse is r cross r, which we could write as r squared. So does this sound true? So x is positive, y is negative. That implies that add them together and you won't get 0. And not that you won't get 0, but that you can never get 0. If x is positive and y is negative, you can never get 0 when you add them together. That sounds false to me. I think I can find a counterexample. Let's see. So I'm looking for a counterexample. So I'm going to pick an x and pick a y such that this right here is false. But I still have to pick x and y according to this first part. So pick x greater than 0 and y less than 0 such that x plus y is equal to 0. That's what I'm looking to do. So let's let x be 1 and y be negative 1. X is greater than 0, y is less than 0. Then x plus y is equal to 1 plus negative 1, which equals 0. And my statement said that x plus y can't be 0. Here I found a case where it's 0. So I have proven this false with a counterexample. And this is 3b. So what I've actually done is I've found an existing x and y such that my propositional function is false. I found a case where x plus y is actually equal to 0, which is the negation of this propositional function. Okay, let's look at some more. Here is 3c. Is the statement, for all w, there exists an x such that w plus x is equal to 0? And the domain of discourse is R cross R. Is this true or false? Okay, so let me think about this. I'm saying that for every w, there is some x that when I add x to w, I'll get 0. Am I able to find something? This sounds like it could be true. Let's see if I can find a way to make this work. So I'm looking at there exists a w for all w there exists an x. So we're in this case. So what I want to do is I want to let x be some arbitrary number, and I want to see if I can find a y that maybe depends on x so that this statement is true. Let's let w be an r, be arbitrary. And then I'm gonna, because I have to make this work for all w. So I'm saying w is some arbitrary number that's in the real numbers. And it doesn't really matter what it is. Then I'm gonna let x be negative w, which is also in r. If w is in r, then negative w is also in r. And this x depends on w, and that's okay. Then w plus x is w plus negative w, which equals 0. So I've shown that it doesn't matter what value I pick for w, I can find a value for x, namely negative w, that when you add w with that number, you get 0. So this is true. This is 3c. I'm going to go write that up in my box. This one was 3c. Okay, next one, D. Is the statement there exists an x such that for all w plus x is equal to 0? So this is a similar statement to last time, except we've changed the order of there exists and the for every. So what I'm saying is there exists x such that for all w plus x is equal to 0. Is that true? So I pick a value for x that'll work for every single value of w. And I'm not sure that's going to be true. But let's look at the negation. Sometimes it can be helpful to look at the negation, especially if we think something might be false. So let's look at the negation. The negation of this one is for all x, there exists a w such that w plus x is not equal to 0. So for all x, there exists a w such that w plus x is not equal to 0. Let's think about this. So x could be 0, or x could be not 0. Because this has to work for every value of x. So here is every value of x. X can either be 0 or x cannot be 0. That's all the values of x. This is all x. Well, what happens in each of these cases? In this first case, let's let w equal 1. Then w plus x is 1 plus 0, which is not equal to 0. So this is true. I've shown that this so far is true. Let's look at the next one. Let's let w be 0. Then x plus w is whatever x is. X is not 0. It's some other number. And then w is 0, which is not 0. It can't be 0 because I said x can't be 0. X is some number that's not 0. So I've shown this is true as well. So for all values of x, I've been able to find a case where this is true. So I've proved that the negation is true. If I've proved the negation is true, that means my original statement is false. So this is one way to approach this problem. So this was, come back up here to my table. 3D was this one. And I looked at this negation, which was up here. I found, I didn't really let x be arbitrary, but I did cover every single value of x. This for all x means when I look at my examples here that I'm doing, I have to cover every value of x. So if x is 0 or x is not 0, I was able to find a value for w such that this was true. And since all this green work was the negation, and I proved that the negation is true, that means my original statement is false. Let's look at 3e. Is the statement, there exists an x such that for all y, x times y is 0? Is this one true? My domain of discourse is still r squared. So there exists an x such that for all y, there exists x such that for all y, x times y is equal to 0. We kind of tried to do this last time. Basically, what we tried to prove last time is that no matter what x is, we can always, no matter what y is, we can always add something to it and to get 0. And in this one, we're trying to do that same thing. There exists an x such that no matter what y is, I can always get 0 when I add. And that's true, I think, because 0 times anything is 0. There's no number like that up here where like you pick something and then there's always something that'll make that thing 0, like there is with multiplication. So I think this one is true. Let's see if we can prove that. Let's let x be 0. Then for all y in R, 0 times y is equal to 0. So I've shown that regardless of whatever value I pick for y, I can always multiply that by something to get 0. So this one is true. This was 3e, is this one. I've done that one. All right, 3f. I guess to go back and explain a little bit more the difference between these two, what I'm doing here is I'm picking this first one first. So in E, I picked the value of x first, and now that will work for every value of y. So I picked the value of x here to be 0, and then it doesn't matter what y is. It doesn't work up here because if I pick the value of x first, it's not going to work for every value of y. It's only going to work for the value of y that's the same as x. It's not going to work for every y. So I guess that's kind of the difference between these two, is you have to pick that value of x first that works for every value of y. That's kind of goes back to what I was saying where the order matters. Okay, let's move along to f. I think I'm ready to move along to f. Is the statement there exists an x and there exists a y such that x times y is equal to 10? Is that true if our domain of discourse is z plus cross z plus? So z plus, in case you forgot, is positive integers. 1, 2, 3, etc. So I'm picking two positive integers and I want their multiplication to be 10. I think this is true. I think I probably could find multiple examples, but I only need to find one. Find one example. I'm going to find two just because I'm an overachiever. So here's example 1. Let x be 10 and y be 1. Then x times y is 10 times 1, which is 10. So that works. Here's another example. I think this is the only other one. Let x be 5 and y be 2. Then x times y is 5 times 2, which is 10. So that's another example. Actually, there are 2 more examples, and those are the opposite of these. So x can be 1, y can be 10, x can be 2, y can be 5. So there are 4 different examples that you could give here. You only need to show one, but I like to show that sometimes there are multiple examples available. So this one is true. 3F is this one. This is one of the easier ones to prove. There exists, all you have to do is find one x and one y, such that this works. Okay, next up is 4G. Is the statement there exists an x and there exists a y such that x times y is equal to 11, where x and y are integers, and they are greater than 1. Are integers that are greater than 1? I think this is supposed to be that. That are greater than 1. Is that true or false? Let's think about this. So my domain of discourse here, x has to be greater than 1 and y has to be greater than 1, and x and y are in the set of integers. So let's see. 11 is a prime number, which means its only factors are 1 and 11. So there's no way to get to 11 with integers and not use 1. So I think this is going to be false. So let's prove the negation is true. Let's prove the negation is true. And the negation is for every x and every y, x times y is not equal to 11. And my domain of discourse is, well, maybe I'll write it like this. I'll say this. X and y are both greater than 1, and they are integers. So let's see. I'll write some of the things I've already said. Positive integer divisors of 11, which is prime, are 11 and 1. And 1 is not greater than 1. I can't find x and y in positive integers and have x be greater than 1 and y be greater than 1 such that x times y is 11. So this one is false. There are no other factors of 11 other than 11 and 1, and I'm not allowed to use 1, so I cannot do this. So this one is, back to my table, 3G. Okay, let's move along to example 4. Turn my page. Example 4. Express the following statements using mathematical and logical operators, propositional functions, and quantifiers. The domain consists of all integers. So my domain here is z plus squared, maybe, because we're doing two things. The sum, part A, the sum of two negative integers is negative. Let's see, the sum of two negative integers is negative. Well, so I know that x and y are both less than 0. They're negative. Another thing I could say is that my domain for this one is z minus cross z minus, negative integers. I'm looking at the sum of two negative integers is negative. So for all x and all y, x plus y is less than 0 when x and y are less than 0. Okay, so I think this is probably true. This is, oh, that's not a very good true. True, question mark. This is like the first one I did. The sum of two positive integers is positive. The sum of two negative integers is going to be negative. So let's try to prove this one. Let x and y be arbitrary negative integers. That's what I'm supposed to do. Start off with something that I know. If x is less than 0 and y is less than 0, let's add y. Add y to both sides of number 1. Do a little plus y. So that leads us to x plus y is less than 0 plus y. And since y is less than 0, 0 plus y is less than 0. So I can rewrite this as x plus y is less than 0. I'll write my little therefore. So this statement is true. 4a is that top left-hand box, which I think we already did 3a in there, so this 4a also goes in that box. Next one, the difference of two positive integers is not necessarily positive. I'm going to rewrite this so that it's better suited to writing the statement with our logical operators and propositional functions and quantifiers. The difference of two positive integers is not necessarily positive. There are two positive integers such that their difference is not necessarily positive. So let's say it's less than or equal to 0. That's not necessarily positive. So what I'm saying is there exists an x and there exists a y such that x minus y, their difference, is less than or equal to 0. Where my domain of discourse is z plus cross z plus, two positive integers. So there exist two numbers that when I take their difference, I'll get something that's either 0 or less than 0. Well, that seems like that's totally true. Let's see if I can find two integers. So here's my example. And here there are so many examples, not like the other one we did where there were like the 4. Here there's like a bunch of them because there are so many negative integers. Let's let x be 1 and y be 2. Then x minus y is equal to 1 minus 2, which is negative 1, which is less than or equal to 0. So as long as, I said negative 2, but this is supposed to be positive 2. As long as you pick a y value that's bigger than x, this will work. So this one is true. There's an infinite number of examples you could do here. And this was 4b. Let's take a look at example 5. Let the domain of discourse be the real numbers. Define p of xy to be x over y is equal to 1. What is the truth value of each of these? My domain here is real numbers, so r squared, or you could do r cross r. What is the truth value of, for all x and all y, p of xy? So for every x and y, this is true, that x over y is 1. Well, that's definitely not true. This is only true when x and y are the same. So it's not going to work for every x and every y. Let's show that the negation is true. We can do this, which means that there exists an x and there exists a y such that x over y is not 1. That's going to be our counterexample. Counterexample. And again, there are so many things we could pick here. I might do the same one I did last time. Let x be 1 and y be 2. Then x over y is 1 over 2, which is not 1. So there's my counterexample. So I've shown this to be false. As long as you pick an x and a y that are both real numbers that are different from each other, this one will be false. Let's look at b. For all x, there exists a y such that p of xy is true. So if you pick every single x value, there exists some y that will make this true. I think, let's look at the negation. The negation is there exists an x such that for every y, x over y is not equal to 1. So am I able to prove that this is true? If I pick a value for x, then this will work for every value of y. And I think it does. Let's let x be 0. Then x over y is 0 over y, which is not equal to 1 for all y. So it doesn't matter what value of y. I picked the value of x first. I pick x to be 0. And then for every single value of y I try, this is going to be true. And this is the negation. So I've shown that the negation is true. So that means my original statement is false. And I think this is the only way that this works, is if you let x be 0. If x is anything else, then this isn't going to work. Okay. So I guess what I could do for this one is, if my domain was all the real numbers except for 0, then this statement will be true. But if I'm allowed to pick 0 for x, then this statement is false. Next one. There exists an x such that for all y, p of xy. So I pick a value for x that'll work for every single value of y. And I think that that's not going to work. Let's look at the negation. For all x, there exists a y such that x over y is not equal to 1. And let's see if I can prove this one to be to be true. If I can prove this is true, then my original statement is false. Let's let x be, I have to pick x first. Let x be an arbitrary real number. Whenever you're looking at for all x, you're using this arbitrary real number verbiage. So I think I'm going to do the two cases again. I did one like this before. If x is 0, and then if x is not 0. X is 0, if x is not 0. Then I want to pick a value for y that this is going to be true, this one right here. So let's let y be 1. If y is 1, then 0 over 1 is 0, which is not 1. So in this case, the negation is true. That's not a very good y. Let me fix that. If x is not 0, let's let y be 2x. Then x over y is whatever x is, which is not 0, over 2x, which is, cross this out, 1/2, which is not equal to 1. So this is also true. So since I've proved the negation true, regardless of whatever value I have for x, my original statement is false. So I don't think we've done one like this before. This is 5C. And that is this one we haven't done yet, 5C. Oh, actually, we have done this one. This is 5C. The one we did right before this. This was 5B. The one that we did right before this, we proved that that one was false. Okay. I think we are on to the last one. D. There exists an x and a y such that p of x is true. So I think this one is probably going to be true. There exist some values that'll make this work. This one is often true. True. Let's check it out. Let's find one example that this works for. So here's my example. Let's let x be equal to y be equal to 1. Then x over y is equal to 1 over 1, which is 1. So here it is true. You don't have to pick 1 here, but as long as x and y are the same, this will work out. And they're not 0. If they're 0, then you have x 0 over 0, which is not good. Okay, and I think that is the end of this section. We'll see everybody next time.